Okay, so or delay start. Thanks so much for coming. So yeah, very pleased to present Scott from Agritech at the moment. Yeah, so before that, some very interesting stories. So yeah, great. Thanks a lot for coming along. Sure.
Yeah, thanks for your patience while we figured out interesting stuff. So back more than a decade ago, I was working as a professor in the U.S., and in the U.S., you're on a 9-month contract. You don't get paid in the summer when you're teaching. So looking for a summer job, I applied to NASA, and I got in. And so that led to a lot of fun, which I'll talk about. So I think most people, when they think of NASA, they think of the space shuttle launching from Kennedy in Florida, but NASA actually has quite a few research centers. And the NASA, the first A is aeronautics, which is where I work, and that was out in what's now NASA Armstrong Flight Research Center in the Mojave Desert in California. Okay, so why is that there? There's a big giant lake bed. I think it's just shy of 10 kilometers across. So at some point in history, that was a lake. It dried off. And it almost never rains there, which is another reason why it's there. You have 360 good flying days a year. When it does rain, the wind blows it across and it evaporates and the dirt's nice and smooth and hard. So it's a giant runway. So if you want to test experimental airplanes and spacecraft and you're never quite sure what's going to happen, that's a great place because you don't have to worry about hitting the runway when you land. Just anywhere there. So that was the original landing site of the space shuttle in the early 80s. The control systems they had with 1970s era technology, they weren't too sure about hitting a runway coming back from space, so they landed out there on the dry lake bed. And then they have to put up on the back of a 747 to take it across the country to Florida for the next launch. Okay, so at the time I was there, this is some of the research aircraft they had. So I mentioned the 747 with the struts there for taking the space shuttle across. Some supersonic research with the SR-71. They're still doing research on how to make sonic booms quieter. So hopefully one day there will be supersonic transport after the Concorde and be able to get other places a lot faster. And various others modified aircraft. NASA does not buy new airplanes. They always buy used. So it's cheaper. So a lot of the F-18s from the Navy, they like to get those because after so many carrier landings, they retire them even though the rest of the airframe is perfectly good, just the landing gear are a little beat up. Okay, so I was there over 3 summers. I got to see the Space Shuttle Endeavour land when there was bad weather in Florida. The Space Shuttle at that time could land up the runway in Florida, but only if there's clear weather. So that was interesting because has anybody ever heard a sonic boom? Few people have. The space shuttle sonic boom is really loud because it's probably going about Mach 10 by the time it passes through near where I was. So my wife was 50 kilometers away sleeping in the morning and it woke her up. And then that NASA Dryden, because it's in the desert, is part of the supersonic land corridor where the military is allowed to fly supersonic for test flights. So I'd be in the building and start shaking. I'm in California, like, is that an earthquake? No, just a sonic boom. Then I moved here and realized those weren't sonic booms. I got to do a test flight on the DC-8. NASA is still flying that DC-8. It was in Christchurch just a few months ago. So you probably can't see it in the picture, but a bunch of the windows are taken out and there's probes sticking out of that, and it measures pollution in the air. So for that flight, we flew over the San Joaquin Valley, measuring the pollution from the agricultural fields. What they mostly do now is they fly from California to Korea, to Christchurch, to South America and back. So they're traversing over the oceans and they're measuring what's in the atmosphere over the oceans. And yeah, and then so people ask me, why did you get to work on at NASA? Was it the rocket, the space shuttle, an airplane? That was this big bus. That was my project. It was one of the lowest of low-budget projects. It was a tour bus from SeaWorld that they had bought. Again, they never buy anything new. It's all used. Built up the superstructure, souped up the engine, could go 160 kph down the runway. So we'd go as fast as we could with the pressure sensors and take data on that. Okay, so why is NASA studying a bus? All right, so the project was to look at some fundamental physics that have relevance to space vehicle design. The little electronics part, electronic pressure transducers. Again, this was a while back, so our little signal box could only interrogate those 64 sensors about once a second, as fast as it could go. Nowadays you could probably buy an Arduino and some kit that could do that. So we're looking at the aerodynamic drag in the wake region of something that's flat in the back, so not tapered like an airplane. Okay, so why are you interested in that? Well, pretty much any rocket ship has this thing on the back called an engine, right? And so that creates this flat area where there's a lot of aerodynamic drag and vortices. So this one was the X-38. It was designed to be an escape vehicle for the International Space Station, because NASA won't put more astronauts on the space station than it could evacuate in case of emergency. The Russian Soyuz capsules only hold 3 people. And it takes basically 2 people full-time just to keep the space station running, just to do all the maintenance, check all the computers, fix everything. So if you only have 3 people on there, that doesn't leave you a lot of time to actually do research on the space station. That project, though, eventually got canceled. X-34 was a technology demonstrator, got canceled. X-37, that one was kind of cool. This one was a bit of a James Bondy type of one. You would launch down to space in a rocket, so it would be in one orbital plane around the Earth. Then it had its own engine and fuel, so it could launch and go into another orbital plane. So you could potentially launch 2 or more satellites off of that for the cost of one, or try to capture the other guy's satellites and that kind of thing. That one was canceled as well, and the Air Force took it, and they've been flying it. If anybody's followed space news, this thing has set the record for the longest time of something in space to come back down and be reused. I think they had it up there for almost 2 years. Doing what, they won't say. But the Air Force recycles everything. They don't throw anything away. And this was the X-33. That was going to be the replacement for the space shuttle. So the space shuttle, remember, was supposed to be an advance over the Apollo rocket boosters where what was it, Chris? Is it something like 5% of the mass was the part that 2% actually went to the moon? Yeah. So the space shuttle was better, but you still had the fuel tank that was burned up, and you had the rocket boosters. So this was the idea, using advanced lightweight composite materials, advanced linear aerospike engine. The whole thing would go to orbit and come back down, so nothing would be reused. Like most government contracts, it was way over budget and way behind schedule. So they canceled that too. Yes, all 4 of these were canceled. Yeah, so all the big projects my project had relevance to were canceled. I was told one of the longtime people at NASA had never worked on a project that was actually completed. Part of being a government organization, every time there's a new president in 4 years, they may say, oh, we don't want to do anything the last guy was doing, and cancel it. So those type of fun things. And then also just all the meetings you had to go to. The Air Force still has that, but they didn't fly it. Now, when I was there, was when Columbia was destroyed, which was quite a sad thing. So they put out a call for proposals for things to make the space shuttle safer. And one of the things my branch chief was proposing was in the back here to put an inflatable thing that would come out and cover the back of the engines to make it more aerodynamic. And if that had been funded, I would have got to work on that, but it wasn't funded, fortunately. Okay, so in terms of the physics, what we were looking at is it's basically the golf ball effect. If you modify the front of a vehicle and make it rough, you can make it transition to turbulence so that the flow covers up the back better and reduce the total drag. So by making the front rougher, you can reduce the drag on the back, and so it'll lose the total drag on the vehicle. And you want to try to get in that sweet spot where it has the less drag, so it has more maneuverability as it comes back to Earth and better chance of landing safely. So this is some historical data. You can see the space shuttle is reasonably close to the bottom of that bucket in its design, at least for that particular vehicle. Okay, so my part was taking the data from going down the runway, analyzing that. I'm not sure if it's still true, but at that point in time, MATLAB was the default tool for NASA. Everybody used MATLAB. So I did MATLAB, having done Fortran programming before. It was nice to actually be able to make graphs when you program. They use MATLAB for their experiments. They had the real-time signal processing toolbox, and we used that for some of the flight experiments. Doing some curve fitting and averaging, figuring out the total drag on the vehicle, and then, of course, mechanical engineers. Once you run an experiment, what else do? You do a computer simulation. So we also did the CFD simulations, which this just shows the very back of the bus. There's some ground effect in the weight coming off of that. So we could simulate that flow field as well. Got some money from NASA to have a grad student do that. And yeah, that's some data. Yeah, it's data. Okay, so that was my first 2 years. My last year at NASA, I got to work on something else, and I can't show you the pictures because it was commercially sensitive. They didn't let me take it all home. They took my computer and wiped the hard drive and all of that. Fun thing about working at NASA, you're not allowed to take any files home. So when I went home at 4 o'clock and there was actually a bell that rang, I was done. I can't work. So that was different than any of the other jobs I've worked. That was nice. So the other one's probably more of interest to you as electrical engineers, and that's adaptive flight control systems. So the motivation for this goes back to the Sioux City crash in 1989. Anybody know how they managed to get the plane on the ground with that one? Because the engine and the tail exploded. It took out the primary, secondary, and the redundant hydraulics, so that they had no controls. The pilots were there turning the wheel and nothing was happening. So one of the pilots, in frustration, grabbed the throttles and started moving them from the other two engines, and they were able to steer the plane with differential thrust. If you go faster, you can go higher. You pull back, you go down. And so they were able to control it. Now, because of the damage to the plane, it wasn't symmetric. The one side had more drag, so they could only do right turns. So if you can pull up the flight path for that, and it's a sequence of big turns until they finally got down in Sioux City on that. So it was very amazing that he steered the plane with no control surfaces, got it landed. Now, because they had no control surfaces, they didn't have flaps, they didn't have air brakes, they couldn't stop once they hit the ground. So he did land on the runway, which saved a lot of people, but the crash killed about a third of the people on the plane. Now, the motivation for that is coming, though. The pilot manually, by trial and error, doing the throttles, kind of taught himself how to control it, because they had about half an hour before they came down. But the thought is, okay, now what if we had a computer program that could do this? So we have an airplane that sustained damage, so it's no longer flying the way it was originally designed. So first of all, it needs to get some input, it needs to learn. So using a neural network type of programming, as it's flying, it's going to record the motions as you do things with the throttles, and then from that learn what it can do to control the airplane. So then when the pilot's there trying to control the steering wheel, the neural network then will reprogram, in this case the throttles, to fly the airplane, to give it some control. And so where that could have been applied was after 9/11, the crash in Queens, where the vertical tail fell off an Airbus plane due to a failure in the composite. That one, from the flight data recorder, it was 8 seconds between when that happened and the plane lost control. Not enough time for the pilot to figure out how to steer it with just the throttles. So when the tail came off, it did a lot of damage. But if you had a computer, then that could reprogram the plane, could have possibly saved that plane. And then another one was when the U.S. was in Iraq, in the Iraq War, a terrorist shot a plane with a missile, took off part of the wing and also took out the hydraulic system. The pilots were able to land it in that one safely. But again, that's a lot of stress on the pilot. You could come up with a computer system that could do that. So that was kind of what we're looking at in this. And the military, of course, also had interested in for battle-damaged aircraft. So my part was our model plane was a Boeing 757. So I had the computer diagram with all the 3D schematics of that plane, which is a really interesting plane. If you fly out of Christchurch, you're probably flying on an Airbus. If you get to look at the wing is straight. A 757 wing actually twists down at the wingtips due to the aerodynamics, so that's harder to build. So what I did was, in MATLAB, I had that model, and I started chopping off sections of one wing, going inward more and more and more, and then ran that through a computer simulation to see how that would fly. It's create a database that could then go into their flight control system. So that was kind of fun. I don't know if they ever actually used that one. But it was, again, it was part of a broader project on this adaptive flight control. One of the ones they used this was for autonomous refueling for the military airplanes where the tanker goes and they fly behind it and refill the fuel tanks. It is actually the most dangerous thing military airplanes do. That's when they lose most of their pilots. So NASA created a system. It used a GPS to get close, within a reasonable distance, and then from there a computer vision system to find the fuel probe and fly the plane into it. The other one they looked at was formation flying. So if you're transferring airplanes across the country, it takes a lot of fuel. About these weak gut vortices, right? Birds fly in formation, and you see the ducks flying. I guess here they'd be going north. In the U.S. they fly south for the winter. So if you can get one airplane in the wing cut vortex of another, you can reduce the drag. Use that flying information. I know that's quite a challenging thing for a pilot to do for hours and hours, flying across the country. So again, computer controls. All right, so after that, I went back to my university, and this is where Chris and I's interests crossed, because we ran into each other at the Air Force Museum, volunteering on rocketry there. So we did a summer program for students from underrepresented groups, the inner city in Peoria, Illinois. So trying to get people who don't normally go to university to think about majoring in engineering. And we had rocketry as the core thing, so I can use some of the stuff I learned from NASA in there. So it was a week-long camp. In this case, we had the wind tunnel. The students would build their rockets, test in the wind tunnel, get the drag, put that in a computer program. These were secondary school students, so we didn't expect them to do all the physics and the simulation. We wrote the code and then let them use it. And then we went out to our American football field. They have the cart, they pick the angle, and they try to launch it through the goalpost and score a try. And you can do that reasonably successful. Now, once you have a wind tunnel, there's lots of fun things you can do. So I had the brilliant idea one year we're going to make a little model wind turbines. That's what my students are holding there. And test them in the wind tunnel. Still got a little DC motor used as a generator. Now, of course, as engineers, we should always do calculations before you actually, build stuff. This is one case where I failed to do that. I'm like, oh, we'll just, get these grunty little DC motors in there. They're cheap, and we'll throw that in there. Okay, now, when you make a wind turbine smaller, there's something that changes in order to keep the physics working. Anybody know what needs to change? They have to spin faster. Okay, so the giant ones you see like up in Marlboro are going pretty slow. When you get down to this size, if they're at peak efficiency, it's 10,000 RPM. I didn't bother to calculate that. The DC motor actually survived with the little bearing in the back here. We kept melting those. They were only $3 motors, so we went through a lot of them. Yeah, so always do your calculations first before you buy stuff. And we did the little black tape as we put a strobe light in there to measure the RPM, and it was in fact 10,000 for the well-designed ones. The poor ones we didn't have to worry about. So that was that one we made on a CNC machine. We also did some rapid prototyping ones, but the surface finish on the rapid prototyper could be a problem on some of these. Wouldn't give you very good aerodynamics. And you also learned that the aerodynamics for a small wind turbine is not the same as what gives you good aerodynamics on a big one. So lots of fun stuff we did with that. Also trying to figure out what I could use for a load to dissipate that without burning up my load too, because we need to vary the resistance to get the sweet spot. Okay, and that one was already there. Okay, so then I had sabbatical. I moved to New Zealand and decided to stay here. So I'm out at Lincoln now doing agricultural stuff. So a big change from rockets. So this, does anybody know what this picture is of? Yep, that's a kiwi fruit orchard. This is late winter when they're spraying hydrogen cyanamide, which causes all the flowers to set buds so they get a lot of kiwi fruit. Hydrogen cyanamide is distantly related to cyanide. It's the toxic thing. This is when people get upset about spraying kiwi fruit, this is usually the chemical they're worried about. And you can see a bit from our fluorescent tracer dye that most of that spray is not landing on the target. And because they're spraying in winter, there's no leaves, so most of it just goes through, because they just need to get a little bit of chemical on those flowers to make them set, so you don't care so much what they're wasting. Measurements that we've taken show about 10% of what you spray actually lands on that 90% going off. So that's the project I'm working on now with Paul. We're trying to make that a lot better. So this is now where we start to get into some more electrical engineering. Different ways we can use sensors to improve this. This is a bit of an older unit now, a SICK LiDAR, like the type they use on the early self-driving car prototypes. So this one, the laser beam scans back and forth in a plane in this direction. So as the tractor drives along the row, we're scanning the plants, and we've got just enough time between when we scan them and when we get back to the sprayer that the computer can process that and decide which of these nozzles can be turned on and off so that we hit the target. So if there's nothing there, it turns off the nozzle so you're not wasting spray. It's a relatively simple control system, just an on-off one, but we were saving about 30% of chemicals just with that. And from the LiDAR, of course, you can do some computer science, image processing, and separate out what are, in this case, the grapevines we were trying to spray, the trellis rows, and the posts in the ground. You don't need to spray the post. They don't care if they get bugs on them. Yeah, and as I said, our numbers, we were saving close to 30% on that. And then in the U.S., I visited the USDA research lab a few times, and they've had a similar idea. They've got a little bit newer LiDAR than we do. This is one of the 360 ones that goes all the way around. Of course, they've got some now that even elevate, so you get close to a 3D picture. And what they've done beyond what we've done is they've got pulse width modulation. So they changed the duty cycle on the valves that open and close the spray nozzle so they can change not only on-off, but they can change the dosage as it goes along. So their LiDAR scanner, when they're scanning these trees, you can say, oh, this is a nice big one, it means a lot. This one is small. We're going to open the nozzle, but only at half strength. So we pulse it open and close to get the spray out on it. Because it's not really possible to change the pressure pump as you're driving along, but you can do the duty cycle on the solenoid valves. So probably relatively simple for you find electrical engineers to program something like that. The agricultural world tends to lag a bit behind the rest of the world in adopting technologies. Because
why on off nozzle not throttling valve, for example?
These things build up deposits over time in dirt, so rumbling valves more likely to get clogged than the solenoid that opens all the way. Yeah.
So it's like that chemical you sprinkle on the trees, they're like emulsion rather than like it's like a.
There's different things that are used. Some of them are emulsions, so some of them are kind of thick.
Greasy.
Mm-hmm.
Yeah, I see.
Some of them are basically water, so those are pretty forgiving. But it depends on what part of the world you're in, the water. In some places in Australia, the well water they get is really kind of nasty. New Zealand, the water, of course, is pretty good here. So, you don't need to do so much with it. Yeah, so with that, so they have the 360 LiDAR, so they can do both rows left and right at the same time with that. So we're still working to try to get one of those kits out here. Being a government organization, they're not allowed to make a profit, so but they can't just give it to me either. So we're trying to get one out here and test it and see if it really is better than ours. Some other stuff we're doing, electronic spray sensors. So most of the sprays are water-based, whether they're an emulsion or something else. So a simple circuit that uses the dielectric properties of water, tells you how much water it lands on that. This is important because most of the time right now when somebody does a spray, how do they tell where it went? Well, they kind of look at the cloud and go, that looks good. Okay, so to actually get some numerical data is a big advantage in agriculture. So here was our test we did out at Lincoln University, just with a real simple sprayer, and we just move these out different distances to see how far we get. And so this is, I was pretty excited by this. This was the real time, so you can see when the sprayer passed, you got wet, we get a signal, It starts to evaporate. This is the next time the sprayer went by. So you can see how much mass you're getting, also when it occurs, what's going on. So we've got some people interested in putting this in their orchards to make sure the spray contractors they hire are actually hitting their plants. There's been stories that, the contractor, they get paid based on how many jobs they do in a day, so they go as fast as possible, and actually setting the spray nozzles wrong and missing the whole thing. Of course, the previous thing I showed you, the automated thing with the LiDAR, would get rid of that problem because it would do it and you're not relying on the person to actually set it. And then this is University of Auckland, final year project team built this box for me. So something a little bit more robust with the circuitry inside a box with a wireless transmitter. So then we could pop that into Google Maps and give you an output of what was being sprayed and how much it got. So something that becomes more of an orchard management tool now. So still working to get somebody to buy this, so still tinkering with it in the meantime. One other fun bit of electronics, lasers. Everybody likes lasers. Lasers are cool. So Doppler effect, you're speeding, the cop's got the radar gun and uses the frequency bouncing off an object to get the speed. So this laser does that, tells me the speed of my spray drops. But it also uses the lens effect, the radius of curvature. The light beams bend, and based on how much they bend, I can figure out the radius of curvature and the size of my spray droplets. So I can use that for spray analysis. And so we've done some wind tunnel testing in my lab. We've tried to do it outside. The problem with doing it outside is these laser beams are less than 1 millimeter in diameter, and they only give you a signal when the spray drop crosses them. So we don't get a lot of data when we go outside. The statistics aren't very good. And when they say it's portable, it's not shown in the picture here. I've got like a cubic meter block of stuff that connects to that. So the U.S. military has a term man-portable. This is about 3-man portable. Man-portable being something one person can carry out in the field. And then the last thing I want to talk about, the project I'm working with Paul Gaynor on, is the electrostatic spraying. So this is where we're trying to make the spray stick to the crop. This is potatoes. So these are charged nozzles, and with that charge on them, they want to get grounded, so they try to get to the literal ground here. On the left side, we turned off the charge, and you can see they just kind of float away wherever, and are wasted. And another fun thing in potatoes, this little bug, which got past biosecurity, I forget the exact year, this is common in North America, the psyllid, eats potatoes, and they like to live on the bottom side of the leaves. So with most sprayers, you spray from the top, you get the top of the leaves all coated with chemical, and the insects down there on the bottom, happily still alive. So one of the fun things about electrostatics, with that charge, the forces on them can actually make them turn around and be on the bottom side, and you can kill those things. So using physics to help us. So back to my laser, measuring the drop size on this thing. I got a peak there of about around 10, less than 20 microns, around 10 microns. These are really small drops that we're getting. And I mentioned that wraparound effect where we try to coat the backside. It's a bit like powder coating. So the mechanical engineering department here at UC has been helping me by running simulations to try to predict where those drops are going and when they will actually make that curve and hit the target. And then the electrical department's been working on a controller, and I've been trying to pull it all together, work on the physics. So going back to NASA, we do aerodynamics. I was looking at big things like a space shuttle. Now I'm sizing it down to micron size instead of 10-meter size. So we have these basic forces, and then now we're adding to this these electrical forces. So of course, Coulomb's law, I have two charged objects, there's a force between them that depends on the charge and the distance squared. Unless they're really close, that force is pretty weak. The image charge force, when the object gets close to a solid, when the charged object gets close to a solid object, it sees a force of a virtual image of it on the other side. So the same type of formula as Coulomb's law there. And so this is the force that actually causes the drop to get captured when it gets to within about a millimeter of a target. More than a millimeter away, and that force is so small it's pretty negligible. Then we have the gradient. So if I'm charging my nozzle to kilovolts and the ground is at 0, there's a gradient kilovolts per meter that is propelling that drop towards the target. And then there is the net effect of all these charge drops together create their own electric field that moves things around. So trying to understand these so we can better design the electrical system. There's been electrical sprayers on the market for a while. We're trying to, of course, take it to another level, doing cool stuff like changing the voltage waveform in real time to see if, like if we put a sine wave through it, we can kind of get pulses and push them even more strongly into the crop. And then some of the electrical work, not showing EV stuff here other than some of the, I think some of your controller bits might be in that picture. So using an apple to see if we get the spray on the back, and then we put a plant and there's a load cell underneath it, so we're actually measuring how much mass we get on the spray to show the effects of the charge. And this one's a leaf wetness sensor. So you can buy these, you put them out in your orchard. Basically, it tells you when you get dew or rain and you get a lot of moisture if you're going to have danger of a fungus disease. They're basically a capacitive plate. So we're been also using that, and that's actually worked pretty well to tell us how much water we get on that. So again, we turn this charge on, turn the charge off, do different modifications of the nozzle to see what's giving us the best deposition. Been having a lot of fun working with the students here at UC on this one, trying to, basically at this point, we're still trying to get enough knowledge so then we can design a better system that will save the world, because we'll only use a fraction of the chemicals, and it'll be great. Kind of that idea. I've got an organic orchard up on the North Island that's talking to me about this. They spray some weird stuff, so we're trying to figure out if that'll work. I think it's like seaweed solutions and other things. She mentioned emulsions. Organic farmers sometimes have to go to extreme lengths to get something that will actually work when you're not using standard chemicals. So it's important to make sure those coat. And some of those things are very expensive too. And I think, yep, that was it. So I'll be happy to take any further questions you have. Yeah.
Just wondering with your spray effectiveness, whether you're taking into account stability of the atmosphere as well?
Good question. So atmospheric stability. So usually denser stuff goes to the bottom, lighter stuff goes to the top, right? So when the air gets hot, it wants to go up. So it tends to happen early morning just as the sun comes up. Because it's been cold overnight, you get an inversion layer. So when you spray into an inversion layer, the spray tends to just hang out in the air. So and you don't want to spray when that happens. But people, I'm not currently looking into that. One of the long list on my long things of things I'd like to do is to have a sensor where you go out and bounce some laser beams off the atmosphere, or have a really long stick that telescopes out and measures the profile and gives you a warning if there's a stability issue. Yeah, if there's an inversion layer, the answer is don't spray. I don't know any other way around it.
Whether it helped spraying in the afternoon?
Yeah, usually spraying in the afternoon is better than spraying early morning. Yeah, some of the worst things was down in Southland, they sprayed on a big mountain. They were spraying to kill wilding pines, and the spray cloud drifted, I think it was 8 kilometers away because of that atmospheric inversion layer. And because it was a herbicide, they know because it killed some other stuff. I guess in theory, if we could really get this electrostatics working fine so all the drops stay within the plants, then it wouldn't matter what's happening above it. But I'd be nervous to recommend that till I had some really good data that it's not going to get up and float away.
Does charging the compound up to kilovolts have any effect on the stability of the compound that you're applying?
I don't know that anybody's looked at that. There are some data that when you charge it, it's more effective at killing the insects and diseases that you want. And that's still a bit of an unknown as to whether there's an interaction between the charge and the chemistry that enhances it, or it's just the fact that you're getting better coverage. Yeah, I mean, I can tell you physically the charge is on the surface of the drops, and if we're using an emulsion like you mentioned, the chemical will be in the middle of the drop, so the two won't actually touch in that configuration.
Can you explain a little bit about how you get the drops on the back side of things?
Let me raise this up.
Oh,
So,
You want to use the whiteboard?
yeah,
Oh, just turn it. You have to turn it off. Then.
you have to turn it off.
Yeah. There's a green button that'll.
Yeah, make sure this says whiteboard. Yeah, had that mistake before.
Yeah.
Yeah, so usually we're spraying, for most things, we're spraying down, right? So physics, gravity just wants to pull it down. So when we have a leaf here, for drops that go within a certain distance, now we've got this electrostatic force on it. So when that force is greater than the force of gravity, right, it can actually make it turn around if it's close. You know, if it's something way out over there, it's not going to see enough force, but within that distance squared, it can turn around and hit the back. So it's a bit like a powder coating process. So one of the things we're looking at, of course, is this force depends on the charge on the droplets, and we're looking at how we can modify what's going on up here to get more charge on the droplets. I didn't get to drop it there. Okay. So, yeah, we've had this question come up. Most of the ones I've seen do not have a special earth. I think they just assume it'll get through the tires, getting tired. I have seen a few that have a little cable dangling on the ground. Yeah, even though it's kilovolts, it's only microamps, so there's not a lot of charge. Yeah, probably best practice to earth it, yes.
Is there any applications to asthma inhalers as well?
I haven't seen it on that. Part of with inhalers is you need the drops to get into the lungs, right? So if you put a charge on it, it's more likely to deposit up here where you don't want it.
Not the modeling, though. I had one question about the rockets. It's about the sonic boom. So I'm wondering if you actually managed to get rid of, I don't know how many you would, get rid of the sonic boom. You must be changing the aerodynamics.
Yeah,
which
so
means you must be changing the actual
there's-
flight control dynamics.
there's a few different things they've done. This might have 15 here. They had one they called Pinocchio, that they put a big boom on it. So the first piece of the airplane that sees the air is going to be the boom. So if you make that piece small, you get a boom off of that, but it's much weaker than the boom you get off the nose. So essentially they spread the boom out. And then another one was they took and they made it almost look like a boat. They redid this nose section here, so it was kind of fatter. And so as the shock waves kind of refract around, kind of smooths it out, so the person down here, instead of hearing a sound pulse that does something like that, right, you get a sequence that kind of is spread out so the intensity is less. Because it's the difference in pressure is what you actually hear. So yes, changing the nose will affect the flight dynamics.
Would it make it easier to control or harder to control?
That I don't know.
Might make it easier, which would be interesting.
so you should do it off the back as well.
Yeah, the space shuttle. When I heard the space shuttle, it's boom boom because you get because it's a flat in the back, you get a big shock off the tail of it. Bullets do the same thing. Usually can't tell the difference in the two booms. Not that you hear a lot of bullets here. Rather than Peoria, occasionally they have still Christchurch.
Incidentally, we did get a sonic boom over Christchurch a few years ago, and a meteor came over the city.
Yeah, not much you can do to make those quieter.
Alright, done. done. So yeah, next day was great. So thanks very much again, and yeah.